The basics of stepper motors are the topic of this video. Much of the development in this video and many of the images come from Electric Motors and Drives by Hughes and Drury. Stepper motors have shafts that rotate in a series of discrete angular intervals. One result of that is that the number of steps taken yields the total displacement. So if it's known how many steps the motor has taken, then it's known what the total displacement of the motor is. This makes stepper motors well suited for open loop position control. Another factor in stepper motor design is that they're designed to hold a position at the rated current, and overheating is when it's stalled is not a problem. So these motors have a high hold torque. Each step in a stepper motor takes a finite amount of time, on the order of milliseconds, but at high rates the motion of a stepper motor appears smooth. There are several applications for stepper motors. A common one would be for small machine tool slides, and here's a picture of a stepper motor driving a lead screw that delivers the workpiece past the tool. Stepper motors are also commonly used for print feeds. And stepper motors have various ranges for step angles and for torques. Step angles range generally from 1.8 degrees to 90 degrees. And this lower limit can be decreased further through driving it in what's called microstepping fashion. We're not going to get into microstepping in this video. The torques for stepper motors can range from 1 micronewton meter for a small wristwatch motor up to about 40 newton meters for a 6-inch diameter motor used for machine tool applications. Three consistent facts about stepper motors, or characteristics about stepper motors, is that they're used for position control. The input to the motor is an electrical signal and the output is position. Or input to a stepper motor system is an electrical signal and output is position. They are digital systems, so the total angle turned through is determined by the number of steps applied. So the output and input are discrete values for the stepper system. And the system is open loop, so there's no feedback taken from the output shaft. And these are how stepper motors are most commonly used, but there are variations. It could be used for velocity control or with feedback on the motor shaft. But typically it's digital position control and open loop. This figure shows the stepping action, and step commands are given to the motor at regular intervals, and the angular position of the shaft increases by steps at those intervals. So the motor is commanded to move 1 step at a time at this rate, and the shaft takes those discrete steps. So we can see a few things from this figure. First of all, that the total angle from the horizontal axis up to this position is governed by the number of steps. So here we have 6 steps. We also see that the average shaft speed, which is the rate of change of shaft angle with respect to time, depends on the frequency of the steps, so how quickly those steps are taken. And we also see that the stepping action is imperfect. There's some overshoot and oscillation with each step. That oscillation time, or the single step period, varies depending on the motor size, the step size, the load, etc. And it's typically on the range of 5 to 10 milliseconds. One more thing that we should note about stepper motors is that positioning is relative. So for an open loop stepper motor system, the total number of steps gives the total displacement since the steps were counted. But if you don't know where the motor was when you started counting, then you don't know its final position in an absolute sense. So for that reason, stepper motors are often driven to a homing position, and then counting is restarted from that position. Slewing is the term used for when the stepper motor is driven at stepping intervals that are less than the single step period. So you can see here at a low rate, the motor has a chance for the oscillations to die out before the next step is taken. And then at higher stepping rates, oscillations don't die out before the next step is taken. And the motor can be driven at high rates. But while for low speed torque combinations, the stepper motor can reach a speed in one step, for higher speed or torque combinations, the stepper motor has to be gradually increased to that speed. And if it's attempted to bring a motor up to too high of a speed too quickly, then the rotor and the stator can be out of sync and the motor will stall, or you'll lose position information. There are three types of stepper motors: the variable reluctance stepper motor, hybrid stepper motor, and permanent magnet stepper motor. We'll look briefly at variable reluctance and hybrid stepper motors, and then spend a little bit more time on the permanent magnet stepper motor. Also in this video, we'll talk about the wiring for stepper motors and the electronics for driving them. Back to this slide, we have three types of stepper motors. The variable reluctance stepper motor is different from the other two types in that it has a ferrous metal rotor. Variable reluctance steppers are good for large steps, say 15 degrees, 30 degrees, 45 degrees. And one thing that's also different is that the current direction is unimportant. So in all the stepper motors, there's a current going through the stator. And for variable reluctance, the direction of that current doesn't matter. And we'll look more at the specifics of these motors on later slides. Hybrid steppers have a rotor that is made up of both steel teeth and permanent magnet. And hybrids are good for small steps. 1.8 degrees per step is the most common design. And finally, permanent magnet stepper motors have a cylindrical permanent magnet rotor. And these are useful for medium to large size steps, so 7.5 to 90 degrees. Contrary to the variable reluctance motor, where current direction is unimportant, for hybrid and permanent magnet stepper motors, the current direction is important, and this can be achieved either through what's called a bipolar construction or a unipolar, and we'll talk more about this later. First, let's look at the variable reluctance stepper motor. The stator is made up of steel laminations, and there are conductive coils around those laminations. This motor design, and shown here, has 6 coils, and they make up 3 phases. So we have phase A, phase B, and phase C. And in this rotor, there are 4 teeth, and these are ferrous metal teeth. And these teeth align themselves with the magnetic field, and that's through the behavior called reluctance. So because there's no magnet here, the rotor isn't polarized, the direction of the current doesn't matter. So regardless of whether the current in A is flowing this direction or it's flowing this direction, the teeth will still align themselves to that magnetic field. When there's no current going through the coils, a variable reluctance stepper motor, the rotor can freewheel. The direction for these steps is determined by the phase sequence. What's shown here is phase ABCA, and that gives clockwise rotation. So you see when phase A is energized, then the teeth line up with that, and now the teeth of the rotor for the next step are equally distant from phase B and from phase C. So whichever phase is energized next is the direction that the rotor is going to line up with. So for the next step, we de-energize A and energize B to get clockwise rotation. So the rotor is drawn to phase B, and then now it's equally spaced between A and C. So if we energize C, then the rotor will continue in the clockwise direction, as shown here. And we can just reverse the sequence to get counterclockwise rotation. So ACBA will give counterclockwise rotation. The hybrid stepper design is less straightforward than the variable reluctance design. The design that's shown here is the 1.8 degree per step design. Some things that we can notice about hybrid stepper design. For this stator, we have 8 poles or coils. So you see the 8 different coils. And on the stator, for a hybrid stepper, the coils are around the steel laminations like in the variable reluctance, but now we have these teeth on the stator coils, or on the laminations. Then the rotor for the hybrid stepper design has teeth on it too, and they're at the same pitch as on the stator. So here's a zoomed in view of poles 1 and 2, and you can see that the pitch for the teeth on the rotor are the same as the teeth on the stator. Now, the rotor has a permanent magnet in addition to these steel teeth, and there's an offset between the teeth on the north end and those on the south end. So say this picture shows the teeth on the north end of the rotor. The center line of these teeth will line up with the gaps for the south end teeth. So a tooth on the south end cap would be here, and another one would be here and here. So they're offset so that the center line for the teeth on this end cap line up with the gap for the teeth on this end cap. And also on the stator, the opposite poles are oriented so that the teeth line up. So 1 and 5 right now line up with the teeth on the north end cap, say. And then for this design, the teeth on poles 2 and 6 and 8 and 4, or adjacent teeth on the stator, are offset by 1.8 degrees. And then down here, the teeth on these poles would be lined up with the teeth on the south end cap of the rotor. Okay. Now some considerations for the operation of a hybrid stepper motor. Unlike the variable reluctance stepper motor, there's a little bit of holding torque even when there's no current in the coils. And that's because the polarized teeth on the rotor are attracted to the metal, the teeth on the stator. And that can be helpful to keep the rotor stationary when the power is off. The coils are arranged in 2 phases. So 1, 3, 5, and 7 are in phase A, and 2, 4, 6, and 8 are in phase B. Let's consider an example sequence to have the rotor move, or have the stepper motor take some steps. Say we begin with coil A energized so that 1 and 5 are polarized south and 3 and 7 are polarized north. In that case, we're in the position shown here, where the north end cap teeth on the rotor are aligned with poles 1 and 5, and then the south end cap teeth, which aren't shown, would be aligned with poles 3 and 7. In order to move the rotor to the next step, we de-energize phase A and we'll energize phase B. Now the direction of current in phase B will determine which direction the rotor moves. In other words, the polarity for coils 2, 6, and 4, 8 will determine whether the rotor goes counterclockwise or clockwise. If, say, we energize coil B so that 2 and 6 are south and 4 and 8 are north, then the rotor will move clockwise, because these north end teeth will be attracted to the south poles on 2 and 6. If we had energized it the other way, then so that 2 and 6 were north and 4 and 8 were south, then the south end cap teeth would have been attracted to poles 2 and 6, and then the rotor would have moved counterclockwise. Now on to the permanent magnet stepper design. And this is the third stepper design, and then we'll look at windings and electric drives. For the permanent magnet stepper design, the rotor is made up of a permanent magnet that is divided into these stripes, and you have alternating polarity going around the rotor. There are two coils in a permanent magnet stepper motor, so the stator is made up of two coils. And each coil will be, depending on the direction of the current, each coil will have a magnetic polarity on one end or the other. So coming from those ends, there are these metal projections that will also have the same magnetic polarity. So these metal projections are close in distance to the rotor, and they will attract the different stripes on the rotor. So for example, if coil 2 here was energized in such a way that this face of it was polarized south and the opposite face was polarized north, then the teeth going to the right would be polarized north and the teeth going to the left here would be polarized south. And so they would attract the rotor into a certain position. This figure shows the idea behind this maybe a little more clearly. Here's coil 1 and here's coil 2. And the magnetic field from coil 1 is oriented so that this is north and this is south. Well, then this projection will have north polarity and this will have south, and they'll attract the stripes on the rotor. So there are two ways that hybrid and permanent magnet stepper motors can be designed as far as the wiring and the coils. They can be made for bipolar operation. That's where you have one winding per coil. For this permanent magnet stepper design, you have one winding per coil, and the electronics are such that you can change the direction of the current in that winding, so that will change the polarity of this coil. The other option is unipolar, and in that case there are 4 windings for this permanent magnet stepper motor. There are 2 windings per coil, and each of those windings goes in opposite directions. So in a given coil, only one winding will be energized at a time, and that will determine the direction of the magnetic field for that coil. So the downside of the unipolar design is that there's less torque because the winding is smaller, since the coil has to hold 2 windings now. But the electronics can be simpler because all you have to do is supply power to one winding at a time. It's not required to be able to change the direction of the current. So now that we've talked about the construction for a permanent magnet stepper motor, let's look at the operation. We're going to examine one particular mode of operation, which is called full step mode. And in this mode, both coils are simultaneously energized. The way we get rotation is by alternating the polarity of one coil and then the next coil. And the step angle can be calculated using this equation. It's 360 degrees divided by the product of the number of rotor teeth and the number of stator phases. Here we're calling rotor teeth the stripes, so each section that has a different polarity would be considered a tooth, and then the number of phases would be 2 for this motor. In this picture we have 16 rotor teeth with 2 phases. One phase or coil is shown by squares, and the other phase or coil is shown by circles. So the step angle for this motor, with 16 stripes on the rotor and 2 phases, is 11.25 degrees per step. Now, in order to get this rotor to move one step, we need to, like I said here, change the polarity of one coil. And so we'll call this coil 1, the squares are coil 1 and the circles are coil 2. So we'll change the polarity of coil 1. So that'll be depicted by swapping the colors here. So every square that's red is going to turn blue, and every square that's blue is going to turn red. So that's supposed to indicate that this end goes from, used to be north and now it's going to be south, and this used to be south, now it's going to be north. So we'll swap the polarity for coil 1 but leave coil 2 polarity unchanged. Okay, so just going back, coil 1 gets swapped, the polarity, so what's red was blue, and coil 2 doesn't change, so coil 2 stays the same. And now if we wanted to move another step clockwise, then we'll change the polarity of coil 2 and leave the polarity of coil 1 unchanged. Okay, so you see that again. Coil 2 gets swapped. And then we'll repeat with coil 1. We'll swap its polarity to get it to move again. And now coil 2. Right. So that's how to get the motor to move in full step mode. One other note on permanent magnet stepper construction, and really this applies to hybrid stepper motors also. So this permanent magnet stepper motor can have either 4 wires, 6 wires, or leads coming off it, 5 wires, or 8 wires. 8 is pretty uncommon, but 4 wires means that it's made for bipolar operation. It can only be operated in bipolar operation. For 6 wires, it could be either used as a bipolar stepper or a unipolar stepper. So for bipolar, we would pass current all the way through both windings, and for unipolar, we would pass current through one winding at a time on the coils. 5 wires has what's called a center tap, where the center of this coil is on the same wire as the center of the other coil. And so it's always unipolar operation. And then the 8 wire configuration is the most flexible. It can be bipolar or unipolar, and the windings can be configured in either parallel or series depending on if it's desirable to have a high current or high voltage drive. The last topic is electronics or drives for generating the current to move a stepper motor. In this figure, we see the ideal current going through each of the windings in a bipolar stepper motor operating in full step mode. So we see here coil 1 of winding 1, it has maximum current going through it, and coil 2 has no current. And then, winding 2 has no current. And then coil 2 winding 1 has maximum current going through it, and coil 2 winding 2 has no current. And then when we want the stepper to move, we're going to reverse the polarity in coil 2. So we'll de-energize winding 1 and energize winding 2. And then when we want it to move again, we'll reverse the polarity in coil 1. So this is the animation from the previous slides. The point for this topic is that the current immediately goes to the maximum current whenever we want that coil to be energized. And when we want it de-energized, it immediately goes to zero current. Now, in reality, we're not going to get this ideal behavior. So there are 3 different types of drive that we'll look at: the constant voltage drive, the current force drive, and the constant current or chopper drive. So here's the constant voltage drive, where the voltage from our power supply gives us the maximum current allowable for the stepper motor that's going through the resistance and inductance of each of the windings. You see here a simplified model of what will happen with the current as a function of time. Instead of a perfect stair wave or square wave, we're going to have a current that follows the step response for a first order system. And the time constant for that system is L over R. So it takes a few time constants for the current to reach the maximum value. And that means that there is going to be less than ideal amount of torque, or less than the maximum amount of torque pulling the rotor. In addition to that, whenever the coil or winding is de-energized, it won't immediately drop to zero current. So when the rotor is trying to move to the next step, there's going to be some torque pulling it or resisting that motion because there's still current going in this winding. So that's less than ideal, and more importantly, whenever the motor is driven at high stepping rates, there's not enough time for the current to reach the maximum current before moving on to the next step. So we just get a small amount of the current going through. And so we, at higher stepping rates, this type of drive has severely diminished current. And because of the magnitude of the time constant, this drop off in torque happens pretty quickly. that is at relatively low stepping rates. So a drive that mitigates these problems is called the current force drive, where we have a high voltage source and we add a resistor in series with the winding, and that's called the forcing resistor, as value RF. So this drive has a quicker response than the constant voltage drive. It gets up to the maximum current more quickly, and it drops back down to zero current more quickly. So the time constant here is L over R plus RF. And that means that for a given stepping rate, there's less fall off. So here, at this stepping rate for a constant voltage drive, we'll have more torque from a current force drive because it can reach a higher amplitude of current in the amount of time, in the amount of stepping time. A drawback to this type of drive is that it's inefficient. There's a lot of heat dissipated in the forcing resistor, and that's especially true when the motor is stationary. So now we come to the third type, which is the constant current chopper drive. This too has a high voltage power supply, so we get rapid changes in current. It's a closed loop system. The system is monitoring the current through the winding. And one effect of this is that it can mitigate the effects of motional electromotive force. And those have been left out in the previous slides. They were just simplified current versus time plots. But the effect of this being closed loop system is that we get closer to the ideal square wave for the current. So because of that, the feedback and the rapid changes in current, this is the standard drive for stepper motors presently. A note on the way it works is that the lower transistor here, so these are typically MOSFETs, but they're shown as BJTs in this figure. Yeah, the lower transistor is on whenever current through the winding is desired. And then the upper transistor is on when the current is below this hysteresis threshold. So when it's below our lower threshold, this upper transistor is on. And then whenever the current exceeds the upper threshold, then this transistor is off, and the current just goes through the flyback diode and dissipates in the windings. And then when it drops below the threshold again, then this transistor turns on. And so we get the current values that are shown here in this figure. This plot shows the pull-out torque, which is the maximum torque that the stepper motor can generate before it loses sync or before it stalls. So here we have the pull-out torque versus speed for a constant voltage drive. You can see the quick reduction in torque, available torque versus speed. The current force drive is better than the constant voltage drive, roughly by a factor of the ratio of RF to R. And then the chopper drive has by far the best performance as far as pull-out torque versus rotor speed, or not rotor speed, but step speed, steps per second. The topics covered in this video were an overview of stepper motor applications and operation, then discussion about the three different types of stepper motors. There was variable reluctance, hybrid, and permanent magnet stepper motors. A little bit closer look at the operation for permanent magnet stepper motors, an equation to calculate the step size for a given motor design, and then considerations for the wiring and the drives to use a stepper motor.